There were two concepts apart from the limitations of Rutherford's theory. There were two other concepts that had come up that led to the understanding that the Rutherford's theory might be wrong. One of them was black body radiation, and the second is photoelectric effect. So it was first observed by Heinrich Rudolf Hertz in the year 1887. So what happened, what he noticed was when light of a particular frequency hit a metal surface, electrons ejected out. So these electrons are also called as photoelectrons, and this effect, where when light of a particular frequency hits the metal and electrons are ejected, is called as photoelectric effect. So this is the apparatus he used. First, you have an evacuated cell with two electrodes. You have two electrodes, and the metal which is showing the photoelectric effect is made the negative electrode. So when light hits the metal, electrons are ejected out, and this leads to the completion of the circuit, and that's how they figured out that there are electrons ejecting out in the first place. And so you have an ammeter. So it is noticed that various metals like ruthenium, cesium, potassium, all of these show photoelectric effect. And they can also show photoelectric effect in the presence of visible radiation. So generally, we will take metals. I won't say, okay, well, let's take a glass of chlorine and observe this particular effect. That's because, as you will learn in the next chapter, our halogens have the tendency, if you recall valency and the concept of valency, you know that electrons, or rather, our halogens have the tendency to take in electrons, whereas metals have the tendency to give away electrons in simple terms. So photoelectric effect is observed only in case of metals because they have the tendency to remove electrons to get a stable configuration. So there were certain observations that were made by the experiments. They are, first of all, the electrons are ejected from the metal surface as soon as the beam of light strikes the surface. This means that the moment light hits on the surface, electrons are ejected out. In essentiality, there is no time lag between the the hitting of the light beam and the ejection of the electrons. So the second one is the number of electrons ejected is proportional to the intensity or the brightness of the incident radiation. So the number of electrons is proportional to the intensity or brightness of the incident radiation. But this does not depend upon the frequency. So there is a particular frequency that is required, but the number of electrons which is ejected depends only on the brightness of the incident radiation. While talking about frequency, for each metal, there is a characteristic minimum frequency, mu zero, zero supposed to be a subscript, below which photoelectric effect is not observed. So suppose let's take, for example, a frequency of mu is getting hit on the on the metal. And this frequency is less than this particular mu zero value. Then no matter, even if you hit that particular substance with that particular frequency, even if you do it, excuse me, for hours, even then electrons will not eject out. So this particular value of mu zero is the what is that, threshold frequency. And so below this frequency called the threshold frequency, electrons will not be ejected out. So no matter, this is even if the intensity of the or brightness of the radiation is high, if the frequency is less than the threshold frequency, electrons will not be ejected out. So at frequency of mu greater than mu zero, the ejected electrons come out with a certain kinetic energy. So the as the frequency, so the kinetic energy of the particular electrons will increase with increase of the frequency, and it is independent of its intensity. So remember this. The number of ejected electrons depends upon the intensity or brightness. Okay, the frequency will determine if electrons have to be ejected out in the first place. That is, if it is less than mu zero, it won't get ejected. But and if the frequency is higher than the threshold frequency, then the kinetic energy of the electrons will increase. So as there is an increase in frequency, there will also be an increase in the kinetic energy, and this is not dependent on the intensity or the brightness of the incident radiation. Okay, so but the issue with all of these observations is the fact that they could not explain these observations were not able to be explained with the normal classical physics that they knew. So according to it, the energy depends upon the brightness of light. In other words, so the number of electrons ejected and the kinetic energy should depend upon the brightness. But as we know, the kinetic energy depends upon the frequency and not the brightness or the intensity of the incident light. So when sorry. So when red light of any brightness shines on potassium for a long time, no electrons are ejected. But when a weak yellow light shines on the potassium metal, electrons are ejected out. So the frequency of red light is 4.3 to 4 into to 4.6 into 10 to the power 14 hertz, and frequency of yellow is 5.1 to 5.2 into 10 to the power 14 hertz. So the threshold frequency of potassium is 5.0 into 10 to the power 14 hertz. So even if this particular light was hit on potassium for 2 hours also, I mean, for an example, even then it wouldn't have led to the ejection of electrons. So there were two things which are not being able to be explained by our classical mechanics. They could not explain the fact that the energy of the kinetic energy of the electrons depended on the frequency and not the brightness, and this meant that there had to be some other thing that was happening. So so all of that we will learn in the videos to come. So in this video, we had learned about the definition of the photoelectric effect, apparatus, and observation of the photoelectric effect, and why photoelectric effect could not be explained by our normal mechanics. So in the next video, we will be studying about the Planck's quantum theory, which acted as an answer to all these questions. Do check it out.